For over a century, modern physics has pointed to a single, terrifying extreme in the cosmos, a region of space where gravity pulls so tightly that nothing, not even light, can escape. Albert Einstein's general relativity gave us the mathematical framework for this phenomenon. The equations describe a space-time curvature so severe that it creates an absolute point of no return. According to the classical model, at the very center of this region lies the singularity. It is an infinitely dense point where all matter is irreversibly crushed and the known laws of physics simply break down. Under this description, a black hole is a cosmic dead end. It is an object of absolute destruction where physical reality goes to die. In 1975, Stephen Hawking complicated this picture. He proved that black holes aren't entirely black. They emit a faint thermal glow, meaning that over trillions of years, a black hole will slowly evaporate into nothing. This created an immediate crisis. If a black hole eventually disappears completely, what happens to the quantum data of every star, planet, and particle that ever fell inside? If that data is destroyed, it violates unitarity, a foundational law of quantum mechanics, which dictates that quantum information must always be preserved. You can scramble it, but you cannot delete it. The root of this paradox lies in a human bias called configurational realism. We instinctively assume that the solid, observable configurations in front of us represent the totality of existence. We equate the destruction of a physical object with the erasure of its information. The laws of quantum mechanics aren't broken. Our definition of reality is just incomplete. The information paradox only exists because we are searching for lost data in the wrong layer of the universe. A framework called the observer-dependent theory of everything, or ODTOE, splits reality into two distinct layers. There is the deep, unobservable space of pure potential, and there are the actualized, physical configurations that we can interact with. Think of the deep potential space as a film strip. It holds all the underlying data and connections. The physical reality we walk around in is merely the screen. We only perceive the temporary shapes projected onto it. Through this lens, a black hole is not a heavy object crushing matter. It is a deconfiguration operator. It is a localized mechanism running the projector in reverse, taking solid physical shapes and returning them to their abstract potential state. The event horizon, therefore, is not a physical wall. It is simply an observational limit. It is the boundary where our ability to measure the physical world stops working. Information is never destroyed because the data never lived in the physical object to begin with. The black hole simply turned off the physical projection, leaving the underlying data perfectly intact in the space of potential. When a wandering star drifts too close to a supermassive black hole, astronomers observe a massive flare of energy. Traditionally, we call this a tidal disruption event, imagining a violent ripping apart of the star by gravity. ODTO reevaluates this event as a cascading deconfiguration. The star's structural coherence drops systematically. It goes from a complex whole to raw debris to elementary particles, and finally back to formless potential. It operates exactly like an ice sculpture melting. The black hole does not smash the star into oblivion. It peacefully melts the structure back into the fluid state it originally came from. This solves another famous problem in physics known as the firewall paradox. Because the black hole is returning matter to a state of potential rather than incinerating it, matter crossing the horizon experiences a smooth, quiet transition. Falling into a black hole is a return to the fundamental source. The physical form ends, but the essence is preserved without violence. This mechanism also clarifies Hawking radiation. Classical physics viewed this radiation as a random thermal leak carrying no meaningful data. Instead, the process is one of stochastic reactualization. Near the edge of the horizon, elements hidden deep in the potential space naturally fluctuate. Occasionally, they spontaneously pop back into physical reality. Because the underlying potential space retains all historical data, these newly formed particles carry the exact correlations of the matter that fell in billions of years ago. The black hole isn't a cosmic eraser. It actively recycles data, seeding the physical universe with preserved latent potential. If this cycle of configuring and deconfiguring governs the life of a single star, it also scales up to dictate the rhythm of the entire cosmos. The Big Bang was the ultimate actualization. Pure, concentrated potential exploded outward, forming every physical structure we can observe. It was the universe's great exhalation. If the Big Bang is the exhalation, black holes are the necessary inhalation. They sweep up spent, high-inertia configurations, so the physical universe does not clog up with its own history. The massive reservoir of unseen potential constantly pushes against our physical reality. This tension creates a steady outward pressure, driving the very expansion of space that we currently attribute to dark energy. The cosmos relies on this perfect equilibrium. Matter emerges from potential, lives its lifespan on the physical screen, and is quietly returned to the source by black holes to be used again. When we stop demanding that reality exists only as solid objects, the universe ceases to look like a place destined for violent destruction. It reveals itself as a flawless, eternal engine of transformation.